The next session we have will be on leveraging MIPI DSI-2 and MIPI CSI-2 in low-power display and camera FPGA-based subsystems. We have the pleasure of having two speakers, Mahmoud Bana, who actually goes by Bana, and Yongdong Sui. Unfortunately, Yongdong was not able to make it live, so we do have a recording. And so Bana's going to start us off, and then we're going to hear from Yudong, and then we also are going to have a live Q&A with Bana at the end. So I encourage you during the presentations, if you have any questions, go to the tab on the right-hand side that says Q&A and type in any questions you have, and we'll cover that at the end. So again, welcome back to MIPI DevCon, and I'm going to pass it on to Bana on leveraging MIPI DSI and CSI. All yours, Bana.
Thank you, Kevin, for the introduction, and thanks everyone for joining this session today. This presentation is about leveraging MIPI display serial interface and camera serial interface in low-power FPGA-based subsystems. Let's take a look at the agenda. We will start with an overview of MIPI in display and sensor applications. Next, we will be discussing the system development trade-offs in ASIC and FPGA. Afterwards, we'll move on to the MIPI FPGA market in China, where HME is located. Then my co-presenter Yandong will walk us through the features and the use cases of H1D03 FPGA. Also, he will highlight the benefits of integrating MIPI DSI and MIPI CSI on the top of MIPI D-PHY physical layer into this FPGA. Finally, we will wrap up with an overview of Mixel MIPI D-PHY integrated into HME FPGA. Starting with an overview of MIPI specifications, MIPI Alliance has developed over 50 specifications since it was formed in 2003. Those specifications were designed for applications targeting high bandwidth along with low power and low AMI, mainly for mobile devices. The specifications evolved with time to target applications beyond mobile, and they became widely adopted in mobile-friendly applications like automotive, IoT, and wearables, and also used in other applications like industrial applications and biomedical applications. Looking at the MIPI in display applications, the MIPI DSI is widely used in different display applications, especially those which require low power consumption and high bandwidth, like mobile, tablets, and wearables. In this slide, we see examples for systems deploying MIPI DSI. Here is Synaptics virtual reality chipset integrating DSI on the top of MIPI D-PHY and C-PHY combo physical layer. Having a C-PHY D-PHY combo in Synaptics solution helps achieving different bandwidth and resolutions for a wide range of displays. Here is another example on compound photonics using MIPI DSI and AR micro displays, and NXP using MIPI DSI in wearables, which is mainly here Garmin Edge GPS. Moving to the MIPI CSI-2. MIPI CSI-2 is a de facto high-speed camera and imaging interface, supporting a broad range of use cases and application areas like imaging, machine vision, ADAS, and surveillance. Here are also a few examples on systems deploying MIPI CSI-2. Microsoft uses CSI-2 in HoloLens in-depth camera. Perceive uses MIPI CSI-2 in Ergo AI Edge processor. E2V and MS uses MIPI CSI-2 in their image sensor families. And here, JU uses MIPI CSI-2 in its automotive camera video processors targeting ADAS applications. The number of MIPI CSI-2 and DSI-2 devices in a given system has been increasing, whether the application is mobile or IoT or automotive or any other application. This has created demand for bridging solutions. The bridging solutions can help post-processing MIPI CSI and MIPI DSI-2 streams, also to aggregate and split bandwidth as needed based on the application. The bridging solutions are also important to interface processors with sensors and display when the two sides of the link have different resolution and bandwidth capabilities. Later in this presentation, we'll be discussing FPGA-based MIPI bridge in details. Before discussing about the FPGA and how it comes into the picture in display and sensor applications, let's quickly review the main points that the system developer may consider while selecting between ASIC and FPGA. The prototyping cost in ASIC is much higher compared to the FPGA, and that's why the FPGA was widely used in prototyping and providing a proof of concept. While when it comes to production volume, the unit cost in ASIC is lower than FPGA. The development time is longer in ASIC. This is, of course, because of the customization done during the ASIC development. From a process nodes availability perspective, of course, the ASIC has an advantage, but this advantage comes at a cost, which is the foundry availability impact. In the design phase, pre-silicon, there is a lot of customization that can happen in ASIC, while in post-fabrication, the advantage here goes to the FPGA. If you have a highly configurable soft core, then the FPGA soft core can be updated to support new features and function post-fabrication. The end product bring-up time is shorter in ASIC. Basically, it's reconfiguration of the ASIC configuration register, while in FPGA it might need longer time if there is an RTL update or any design update. From a power consumption perspective, the ASIC has an advantage compared to the FPGA. Moving to the FPGA and sensor and display markets, as I mentioned earlier, FPGA in general were mainly used for prototyping ASICs and providing proof of concept. And later in the product lifetime phase, the FPGA is being replaced by ASIC. But this is not necessarily the case anymore. FPGAs are being deployed in end products, and this trend is growing because of having faster FPGA speeds along with decreased power consumption and cost. Also, because of the benefit of having highly configurable soft core, and customization is a king when it comes to bridging applications, for example. The main productization challenges when it comes to FPGA would be the power consumption and the end product realization time. To minimize the power consumption, the developer may balance between the hardened functions and the customizable functions that will be implemented in the FPGA soft core, and probably they will consume more power. Moreover, targeting a newer technology node will help minimizing the power consumption. For the end product realization time, the FPGA system developer may provide a reference design to help the end customer develop their own soft core. So moving to the MIPI FPGA market in China, where Hercules Microsystems is located, there is a growing trend for using FPGA and MIPI bridging solutions, mainly for MIPI DSI and CSI protocols on the top of MIPI D-PHY and C-PHY physical layers. The traditional way to build a MIPI bridging system over an FPGA was to use the FPGA LVDS interface to emulate MIPI interface. But the growing trend here is to harden the MIPI subsystem, including the PHY and the controller, to achieve many benefits. Those benefits are mainly the faster development time, because you don't need to implement the whole sublayer, the MIPI subsystem sublayer on the FPGA, and of course less power consumption. With less power consumption, less development time, this also achieves less time to market. Comparing this FPGA with hardened MIPI subsystem layer. Comparing this solution to the ASIC, the main advantage here is the flexible and highly customizable FPGA soft core that can be updated to support different applications and use cases post-fabrication. Of course, to achieve the desired flexibility, this will require a highly configurable MIPI subsystem that supports the different use cases and applications targeted by the soft core. Now, I will pass it to Yundong to walk us through the features and use cases of Hercules.
Okay, thanks, Banner, for introduction, and thank you all for attending our presentation today. This is Yundong Cui, the Technical Support Director at Hercules Microsystems. Thanks. For the next few slides, I will make a brief introduction on H1D03, a SoC chip that's designed by Hercules Microsystems, which is a FPGA and SoC design company in China. Let's start from the features of this chip. H1D03 is a 40nm LP process node chip, which has 2K Lat6, which is equivalent to 3K Lat4, and the performance is 200 MHz. It also has on-chip embedded memory block and also the DSP block. It supports LVDS interface, which is up to 1.2 Gbps. It also supports LVTTL and LVCMOS of different voltage. One of the most important features about this chip is it has on-chip MIPI D-PHY and MIPI DSI controller. The MIPI D-PHY is licensed from Mixel. And the MIPI D-PHY is a universal D-PHY. It also supports MIPI transmitter and the receiver. For the DSI controller, it can support the MIPI host and the peripheral. So since it has two groups of MIPI on chip, it can support the 2K resolution LCD or OLED display. It also has MCU on chip. The MCU is a single cycle 8051 core, and it also supports the general peripherals like UART, SPI, I5C timer, and DMA peripherals. Except the MIPI and the MCU, it also has on-chip SRAM and also supports the AES encryption for the bit stream. And it also has different package options like W72, W58, and W68. And most of these packages is less than 4x4 millimeters. And in this diagram, it shows different kinds of MIPI bridging application on this chip. As you can see, H1D03 only has two groups of MIPI hardcore, but it can also support using LVDS to emulate MIPI D-PHY, plus some FPGA logic to do MIPI DSI and the CSI controller. So in this diagram, you can see, like for the first one, it can support the MIPI DSI input to MIPI DSI output. It can support up to Full HD or Full HD plus resolution. And in this case, the FPGA can do the scaling and MIPI data processing, and also some OSD application. And for the second one, it can do the MIPI CSI to DSI conversion. As you all know, the camera data is a little different with different display data. They have different commands, resolution, or the frame structure. But if the camera's resolution ratio is similar like the display, for example, or 16:9, then it is possible to use FPGA logic to do this conversion. Even the resolution is a little different, the FPGA can do the scaling. But if the camera resolution is quite different with the display, for example, you need to do some horizontal to vertical conversion, then the FPGA plus display memory can also possible to do this conversion. Of course, for this kind of application, there are some limitations. Since the frame structure is different with CSI and the DSI, if the display has very strict requirements on the parameters like VBP, VFP, or HBP and HFP, then it is difficult for the display to perfect match the CSI input. For this kind of scenario, it is hard to do this conversion. And for the third one, this chip can also do the 2 groups of MIPI input to another 2 groups of MIPI output. And in this application, it can support 2K resolution for both receiver and transmitter. And for the first one is 1 MIPI DSI input to another 2 groups of MIPI DSI output. And the last one is the input can be some peripheral or some parallel interface like RGB, BT65656 to MIPI DSI conversion. Okay, for the next slides, I will make some introduction on the different kinds of application on this chip, which includes consumer application like cell phone, tablet, MIPI display, bridging, AR glass, the MIPI to KSPI conversion, the e-paper display, and the smart home control panel. And also the chip is used in the industrial application like industry camera. Okay, the first one is cell phone and tablet MIPI display bridging solution. The background of this application is that, as you all know, for the tablet or the cell phone, they have different application processor. There is low end and also high end. Usually for the low end application processor, it can only support Full HD or Full HD plus display resolution, but it might not able to support the 2K resolution. Since usually for the 2K resolution, it requires 2 MIPI interface, 2 groups of MIPI interface. So for the low end, if they would like to also support 2K resolution, some extra processing is required. So here is a solution that using H1D03 can help user to use low-end application processor to support the 2K resolution. For this kind of application, the function of H1D03 is like the first is MIPI receiver using a LVDS to emulate MIPI D-PHY and FPGA logic to do the MIPI receiver. The second is using FPGA logic to do the upscaling, okay, based on FPGA logic and the DSP and also the embedded memory block. The last one is the MIPI transmitter based on the MIPI D-PHY and the DSI controller hardcore. So in this case, with the help of H1D03, even the low-end application processor is able to support the 2K resolution. And here is another application is used in the AR glass. Okay, for some AR glass solution, they need to use a micro LED for the display. And for this kind of application, usually the application processor cannot support 2 groups of QSPI interface directly, but they have the MIPI interface. So the H1D03 can help to do this conversion. Okay, the first one is the H1D03 need to receive the RGB data from the MIPI interface and drive the micro LED with QSPI interface. And the second is it can also increase the display frame rate. This is another advantage of this chip. It can also provide a small package option with PSRAM SIP in it. Okay, with the PSRAM, then the H1D03 can be able to increase the frame rate from 60 Hz to 120 Hz. and the package is pretty small, less than 5 by 5 millimeters. And here is another solution that for the e-paper display. For this kind of application, the background is like you can see several tablets that can support the e-paper display, but the e-paper display has very special requirements on the source and gate driving interface. Most of the application processor cannot drive this kind of interface directly, but with the help of H1D03, it is possible for them to drive this kind of interface. For the first, the H1D03 need to get the display data from application processor through the MIPI interface. Okay, then it has to follow the e-paper display interface rules to drive this display. And except these basic functions, the FPGA can also do some immediate processing, like color mapping and dithering to increase the frame rate or to enhance the image quality. All of this is based on H1D03. It also has a package with a PSRAM sibling in it. So you can use the PSRAM as a display memory. Because for the paper display, they have to compare the difference between the last frame and the current frame. So the PSRAM is necessary for the display memory. Okay. This one is a smart home control panel solution. For this kind of solution, the H1D03 is used to control the whole panel, including the touch part. Okay, it can support RGB or LVDS or MIPI interface, and the resolution can support up to Full HD. It also has a Wi-Fi or SD card interface. One of the most important advantage for this kind of solution is that this is a very cost-effective solution because there are no DDR3 display memory and no high-performance application processor is required. Okay, you can use just one chip to support this control panel, including the touch part. And for the GUI framework, it can support both button, diagram, table, and slide and image, and also support alpha blending algorithm for the transparent effect. Of course, it can support different kinds of language. Here is the example for the H1D03 to do the industry camera. The background for this application is like for most of the main control platform, okay, it can only support the LVDS interface, right? Because most of the sensor is LVDS interface. But some of the main controller cannot support the CSI interface directly. So it needs a conversion from the MIPI CSI interface to LVDS interface. So the H1D03 can help to convert this MIPI CSI interface into LVDS interface using MIPI D-PHY hard IP and the MIPI DSI receiver and or the CSI receiver, and also FPGA to do the CSI decoder and send out data through LVDS interface. It also has the capability to do the data reassembly for customized function. This diagram shows the Hercules Microsystems earned the coveted award for Best FPGA and Processor of the Year at the 2020 China IC Design Achievement Award Ceremony. One of the most important advantage for this chip is that this is a SoC chip with the MCU inside. So it is the MCU can provide the following benefits. Includes the first one is it is very easy to interface with other devices with general interface like SPI fancy UART without using extra FPGA logic resource. And the second is it is more convenient to configure MIPI D-PHY and DSI controllers related registers through MCU. And the last one is it is very suitable for the power management because H1 D03 used a lot in the consumer applications, which is very power sensitive. And the MCU support different low power mode. It can also do the clock management for the MIPI and FPGA different logic resources. So this is a very good solution to do the power saving for the customer.
Today we are looking at a Mixel customer demo from Hercules Microelectronics. This is a human-machine interface, or HMI solution, based on the HME H1D03 FPGA, which can be used for smart home appliances such as refrigerator, ventilator, and air conditioning control panels. In this demo, we see the GUI for refrigerator control. The H1D03 supports MIPI, LVDS, and RGB display interfaces up to 1080p. With an embedded simplified GUI framework run on the on-chip MCU, it can support button, character, diagram, table, and slide operations. The FPGA logic is mainly used for display memory management and image processing such as alpha blending for transparent effect. The on-chip hardened MIPI DSI controller and Mixel MIPI D-PHY support MIPI interface display using less logic and power consumption compared to other platforms. And when compared to SoC platforms that support Linux or Android systems, the H1D03 FPGA supports faster boot and is more cost-effective. Mixel provided 2 instances of our 4-lane MIPI D-PHY universal IP, and HME achieved first-time silicon success.
So I would like to thank Yandong for this walkthrough. Now let's take a look at Mixel's MIPI D-PHY integrated into H1D03 FPGA. It is a universal D-PHY IP supporting master and slave configurations, also supporting MIPI CSI and MIPI DSI protocols. 2 instances of Mixel D-PHY IP have been integrated into HME FPGA. 4 lanes each, achieving 1.5 gigabit per second per lane in high-speed mode and 10 megabit per second per lane in low-power mode. HME achieved first-time silicon success integrating the 2 D-PHY instances. Finally, here's the conclusion. MIPI applications have evolved substantially and expanded with time from mobile to mobile and beyond. MIPI CSI-2 and MIPI DSI-2 protocols are kind of de facto for low-power sensor and display systems. MIPI-based FPGA is useful not only for developing a proof of concept, but also it can be used in consumer and industrial products, reducing the time to market and the development cost. HME's award-winning product, H1D03 FPGA, integrated Mixel IP. This demonstrates the wide adoption of MIPI PHY subsystems in MIPI CSI-2 and MIPI DSI-2 applications. With that, many thanks to all of you for participating today and joining this session. I think we can move on to the Q&A.
Thanks, Bana. Really appreciate it. So I just want to say thank you to Yongdong and Bana for the presentation. It's exciting to see lots of different applications using CSI and DSI, and everywhere from smart home displays to smart glasses displays to industrial cameras. So it's always neat to see where MIPI's applications are landing. With that said, let's go into some Q&As. Let me check on seeing what is being asked. Okay, so you spent a lot of time sharing about MIPI D-PHY integrating into FPGA with CSI and DSI. What other MIPI PHYs do you see gaining traction for sensors and displays?
Yeah, in addition to MIPI D-PHY, we have also C-PHY. It's used independent alone or also used as MIPI C-PHY D-PHY combo. We have seen increasing interest in this IP over recent years, targeting, of course, both camera and display applications. In this particular presentation, yeah, early on I've showed the Synaptics virtual reality chipset. It has been deploying C-PHY and D-PHY combo, and that was a display application. Of course, in camera and sensors, C-PHY and D-PHY are also widely adopted.
Okay, thanks, Ben. And you mentioned you guys are developing the IP for this. Can you share a little bit about what process nodes or foundries that you have this available on or planning to port to?
Sure. We have had the D-PHY IP silicon proven since 2008. It have been ported. We have ported this IP with first-time silicon success in 12 different nodes and at 8 different foundries, all the way from 180 nanometer down to 5 nanometer.
Okay, so that's great. So there's good IP available. So those who are listening, it's an enablement for what you want to do. Another question that came up as well is, are there multiple FPGA products with the embedded or hardened MIPI PHY or controller in it today?
Yes, according to our understanding, that is mainly in bridging applications and mainly in China. We have seen a growing trend over there of FPGAs deploying hardened MIPI subsystems.
Okay, and do you know if there's any plans to? You mentioned that you have integrated the D-PHY that goes. Maybe this is better. Are you seeing anything moving up to the D-PHY 2.0 or the C-PHY 2.0 being integrated or higher? As earlier we had the PHY roadmap going up to 3.0 right now in the specs. So where do you see that going?
If this question going to is about like a MIPI bridging solution, the one we are discussing today, or in general, I would say the answer to both is yes. We see newer D-PHYs and also C-PHYs deployed in those MIPI FPGA-based bridging solutions. And in general, we see high demand on newer versions of MIPI D-PHYs and C-PHY supporting much higher speeds, like 6 gigabit per second D-PHY mode, and similarly in C-PHY mode, but gigasymbol per second.
Okay, that's great. Thank you.